Okay, Precalc C, day before winter break, we did not really finish the hyperbola lesson, like we just barely finished it, but in a good, well planned out class, there would have been like 40 minutes at the end for you guys to slowly work your way through this packet, because I think it's kind of hard. So I'm just making a video now because it just seems like the best way to do it. So here I am alone in a room. Woo, it's so weird. If I try to play music in the background, Google will block me, so we'll just in silence and solitude, I'll do a bunch of math problems. So turn to page 4 of your packet, and on page 4 of your packet, some people in some classes may have just gotten around to starting this problem. Here we have a hyperbola whose foci are at 10, 0 and negative 10, 0. And, oh yeah, and the hyperbola is just like pictured, so let me just draw that in. So, and it's like counting by twos, right? So it's like 2, 4, 6, 8, and 2, 4, 6, 8. And here are the vertices of the hyperbola, here at 8, 0 and negative 8, 0. And here's the foci are here at 10, 0 and negative 10, 0. Okay, and my drawing won't be as good as the one on your packet, but something like this-ish. And here, this is page 4. Okay, so what do I observe about this hyperbola? Well, it's a sideways hyperbola, and the distance from the center to one of the vertices is 8. So basically just like A equals 8, yeah? And also that C is 10. Those are the two real numbers for a hyperbola, but we have also defined b squared to be c squared root c squared minus a squared, or b squared to be c squared minus a squared. So I also get that b is then 6, because just like Pythagorean theorem, you can just like do that one in your head. Good. What does that tell me? Well, it basically just already tells me the equations of the hyperbola. That this is a hyperbola, which is horizontal, so x squared, and the x coordinate has been stretched out by a factor of 8. So this is, you know, maybe it's even better to write it as like x over 8 squared minus y over, well, this 6 tells me that the y coordinate has been stretched out by a factor of 6. So there is my hyperbola, and let's see how much space I have here. Not sure. How much space I need. That seems fine. So okay, what else? There isn't much else really. The eccentricity of any hyperbola is just like an ellipse. It's c over a, and so the eccentricity of this ellipse is 10 over 8. So that's 5/4. Okay, and notice that this eccentricity is greater than 1. And in fact, that's a property of hyperbolas. Just like ellipses have an eccentricity which is less than 1. When it's really near 0, it's almost like a circle. When it's really near 1, it's very, very elliptical. The eccentricity of a hyperbola is greater than 1. Okay, cool. What else? Oh, also a hyperbola has asymptotes. And sort of what we learned, maybe I'll just go through it again, is if you take, say, this hyperbola and try to solve for y, then you get y squared over 36 plus 1. Well, no, I guess I'll like to do it like this. Y squared over 36 is x squared over 64 minus 1. Yeah? And so we get y squared over 36 equals x squared minus 64 over 64. And so really what we have is that y squared is 36 over 64 times x squared minus 64. Sort of just rehashing the whole argument from class all over again. And so what is y? Y can be written as plus or minus, well this is really like 6/8, right? So that's 3/4 root x squared minus 64. And for very, very, very large values of x, so as x goes to infinity, you're taking a really big number, you're squaring it, you're subtracting only a tiny bit from that, and then square rooting again. So that inside of that radical is basically just x. So y is getting really close to plus or minus 3/4 x. which is another way of saying if you plug in a really large x value, your y value is about 3/4 times that. And another way of saying that is that this hyperbola has asymptotes. And yeah, those asymptotes are y equals 3/4 x and y equals negative 3/4 x. And we can go back over here and we can draw those asymptotes. Well, how do I do that? I'll go sort of up 6/8. So and what I'm making now is like this box, man. This box is great. In fact, it's called the happy box. And why is it so happy? Because it's just beautiful. I love it. What is so great about the happy box is, well, what is the happy box, first of all? The happy box is the box, well, it's this box, man. It's this box which sort of has a width. You go out to the vertices and you go up by this number b. It's sort of a way of thinking about what b is. Remember, I'm counting by 2's on this graph, so it's 2, 4, 6. But what makes this box great is the diagonals of this box, because I don't think I talked about this in any of the classes, the diagonals of this box are the slant asymptotes of the hyperbola. And so to make an accurate graph of the hyperbola, you often just make the box, like first. And so, it's hard to read a little bit with red, but this is the line y equals 3/4 x, and this is the line y equals negative 3/4 x. So that's like a thing. And I think that's all they wanted you to do here, right? Yep. Ta-da! These are the asymptotes. This is the eccentricity. This is the equation. Okay. You probably didn't even need me for that. All right. Next one. So much fun alone in a room. Okay. Here we go. You are just given out of the blue y squared over 16 minus x squared over 49 equals 1. Okay. Oh man. And what we want is like everything. Graph the asymptotes. Give the equations of the asymptotes. Graph the hyperbola. There's something about the latus rectum going on. You're asked to take find the coordinates of the foci, plot the foci, eccentricity, everything. Okay, let's do it. Well, first of all, what's going on here? This is like a kind of a y squared minus x squared equals 1 hyperbola. And actually, if you want to be sort of really smooth about this, you could first kind of like just understand on a deep level, what does a y squared minus x squared equals 1 hyperbola look like? Well, that's a hyperbola, well, let's just plug in some numbers. When x is 0, y is 1. So that's 0, 1. When x is, or if x is 0, y could be negative 1. So 0, negative 1. And then y squared is always x squared plus 1. So in fact, if that's the case, since y squared is x squared plus 1, then y is always going to be greater than 1. Y squared will be, yeah. So what does this hyperbola look like? It looks kind of like this. It has asymptotes y equals x and y equals negative x. And this is just like, like this. This is kind of like the most basic hyperbola that there is. This hyperbola is vertical. Yeah, sure. Yeah. So, I guess one other thing we could say is that that y squared will never be sort of 0, right? So y is never going to be 0. So it looks like that. All right. So what is our hyperbola? Our hyperbola is just this unit, vertical unit hyperbola, but stretched out in 2 different directions. The y coordinate has been stretched out by a factor of 4, and the x coordinate has been stretched out by a factor of 7. Okay, I don't know if that was helpful, but anyway, I can now get ready to sort of graph this thing and sort of know a little bit about what it looks like. So if the y coordinate has been stretched out by a factor of 4, so now I got 1, 2, 3, 4, 1, 2, 3, 4. That's where my vertices are going to be. And in fact, you could always just plug in 4 for y, And if you plug in 4 for y, you get 1 minus some stuff equals 1. So the only way for that to be true is that stuff is 0. And so indeed, I have this point 0, 4, and this other point 0, negative 4. Those are the vertices. And in fact, I can just start kind of saying, all right, I know that A is 4. And, well, B is 7. What does this number sort of B tell me? Well, it's how much it's being stretched out in the x direction. And 2, 3, 4, 5, 6, 7. 4, 5, 6, 7. The basic significance of that is that gives me the dimensions of my happy box. Which is really just another way of saying this is sort of how the whole hyperbola is being stretched out horizontally, which also stretches out the asymptotes and everything. All right, so I think that's like the easiest thing to do first is to make the box, which gives me the asymptotes right now. And what are those asymptotes? Well, those asymptotes are y equals 4/7. So 4/7 x, and y equals negative 4/7 x. And notice it's not just like b over a, how some people memorize it, because when the hyperbola is vertical, the asymptotes are actually just a over b. But it's better to just look at the picture and see, up 4/7. Okay, so equations of asymptotes done. I can also calculate c based on the relationship I know between, in a hyperbola, it's always true that a squared plus b squared equals c squared. That's just how we defined b in the first place. And so I can just calculate c. What is c? It's going to be like 49 and 16 is root 65. So that's root 65, which is approximately 8. It's a tiny bit more than 8. All right, so what does that tell me? That tells me that, whoa, it tells me that my picture is not quite big enough because actually my foci are going to be way up here at 5, 6, 7, 8. This is where my focus is. And 1, 2, 3, 4, not quite 8, but basically 8. And in fact, it should look probably better on your picture, yeah, because I gave you much more space on your picture. So what is this point? This is 0, comma, root 65, because that's what c is. It's the distance from the center to the foci, and this is 0, comma, negative root 65. Okay. So what does the hyperbola look like? It must look like this. It kind of hugs close to the asymptote, and then a little bit of this, and hugs this way, and a little bit of this. All right. Now, good. So I know what C is. I have put the, I guess if I want to follow the problem exactly, I should just like say what the foci are. The foci are 0, comma, plus or minus root 65. Good. So I have the foci. Check. I have the asymptotes. Check. What else? The eccentricity. That's kind of easy. The eccentricity in an ellipse is C over A. So that's root 65 over 4 in this case. Okay? That's pretty easy as well. Then there's this sort of other weird reference to the latus rectum. What is the latus rectum? In general, the latus rectum of any hyperbola or ellipse is the chord which is perpendicular. Scoot over a little bit there. Perfect. It's the chord which is perpendicular to the focus. No, the chord through the focus perpendicular to like the main axis of the thing. All right, so in this case, we have a vertical hyperbola. So let's just do it. I think it's easier to just do it in general. So if you have y squared over a squared minus x squared over b squared equals 1, that is a generic vertical hyperbola. So we can sort of plot it. It looks like this. Yeah. And so this right here is 0a, and like et cetera, et cetera. And then basically what I have over here somewhere is a focus. And this focus is 0c. And what is the latus rectum? It's this thing. It's this chord of the hyperbola, I hope that's visible, which goes through the focus and is perpendicular to the transverse axis. Or the line, I guess the line through the foci. Okay, so how do I find the length of that thing? Well, I guess the simplest thing to do is to just say, well, what is that point? Well, I went over a certain amount and up c. So the coordinates of this point must be something comma c. Maybe I'll like zoom in. Although maybe that's a bad idea. I don't know. Okay, so if I want to find the length of that, then I really just need to know what x is. And so, well, what is x? Well, I guess I'll just solve, right? So I want to plug the point, so like basically like plug the point x comma c into this equation and then solve for x. And that will tell me basically what like this length is, which is like ends up that green segment, which is like half the latus rectum. So okay, if you do that, then you're plugging in c for y squared, so you get c squared over a squared minus x squared over b squared equals 1, and now I have an equation which I just need to solve for x. So I get c squared over a squared minus 1 equals x squared over b squared. And really this is just like x squared over b squared equals c squared minus a squared over a squared. And this is starting to look familiar because c squared minus a squared is b squared. And so really I have x squared over b squared equals b squared over a squared. And so x squared is b to the 4th over a squared, and then x is b squared over a. Okay, so what that tells me is that any generic hyperbola, which is horizontal, is going to have this point over here, this endpoint of the latus rectum is going to be b squared over a comma c. And this point over here will be negative b squared over a comma c. So what is the latus rectum in this hyperbola? Again, it should look a little better on your paper, but it's like this segment. And I want to know basically everything there is to know about this segment. I want to know what this point is. And I can tell you one thing about that point already, which is that it goes, I don't know how much it goes over, but I do know how much it goes up, which is 65 because it's perpendicular here. And so this is something comma root 65. And you could just plug in x comma root 65 into the actual equation of the hyperbola, or you could just do it by formula. And basically, the formula says that this is always going to be b squared over a. Well, that's 49 over 4. So that's 49 over 4, which is like about like 12 something. And if you drew your hyperbola decently accurately, you should get that this segment sort of meets up here like around like 12. 12.25. All right, so final result is that the endpoints of the latus recta, I believe they're called, are, well, they're basically at plus or minus 49 fourths, because that one is at 49 fourths, this one's going to be negative 49 fourths, root 65. But then there's the two more down here, right? Because there's like a whole nother latus rectum, just like there, and that's something like plus or minus root 65. Okay, so that's like the basics. I don't know, should I do like one more? I feel like I should do one more. I think most people usually figure this out by themselves, but you weren't in class to like have people to like work on it with, so maybe it's helpful to watch this, but you know, try it kind of yourself. Okay, let's go. Well, this is now page, the next page, so page 5. So what are we told? We're told we have a hyperbola whose foci are at 0, comma 2 root 10 and 0, comma negative 2 root 10. Alright, so 2 root 10 is like root 40, so that's more than root 36. So this is like 6 and some change. Okay, so I can plot this, and if I try to plot this, 1, 2, 3, 4, 5, 6, 7, so 6.5-ish. There's my 1 point, 1, 2, 3, 4, 5, 6, and some change. There's my other point, 0, comma 2 root 10, and 0, comma negative 2 root 10. All right, what do I want to, oh, and then the equations of the asymptotes of the hyperbola are y equals 3x and y equals negative 3x. All right, so that means like slope 3, right? So if that was 6, 3, 6, no, that would be slope 2. So the slope is 3, so that's like, yeah, something like that. And then, harder to draw freehand, should be easier for you on your paper. So here's basically the situation. These are my asymptotes. Y equals negative 3x and y equals 3x. And I want to find the hyperbola which has those foci and these asymptotes. Okay, well, what do I know? I know what C is. C is 2 root 10, or root 40. And I know also that my hyperbola is like vertical. Alright, so and I know that the slope of the asymptotes is 3, which is just another way of saying that that it's been stretched out by sort of A in the y direction, and it's been stretched out by B in the x direction. So the slope of this must be AB, or AB or something. So basically, I know that the asymptotes must have slope A over B, because I have to go up A over B in a vertical hyperbola. So 3 has to be A over B. But then I also have another relationship between A squared and B squared. So this tells me that A is 3B, but it's also true that A squared plus B squared equals C squared in a hyperbola. And so what I also know is that A squared plus B squared equals 40. And basically, that's the whole gist of the problem, right? Anytime you give me any two of A, B, and C, I can always find the third one. And knowing the slopes of the asymptotes gives me the ratio between A and B. And so now I just have a system of equations in two variables I can solve for. So if that's that, I'll sub that in, and I'll get A squared is actually just 9B squared plus another B squared equals 40. So if 10B squared is 40, then B squared is 4. And that means that B is 2. Yeah. So if B is 2, then what's A? A is 6. And that sort of looks about right. That A would be 6, and A would be 6. And if B is 2, then that means that the happy box looks kind of like that. And indeed, these lines are the perfect diagonals of that box. And what does the hyperbola look like? Kind of comes in like that. In this case, the vertex is very close to the focus. Okay, so there's my hyperbola. What else do I have to do? From that point, not much. Just like do all the stuff. So what's the equation of this thing? It's y squared over, well, y has been stretched out by a factor of 6, we just said, so this is y squared over 36, minus x squared over, has been stretched out by a factor of 2, so 4 equals 1. So that's the equation. That's one thing we had to do. Graph the foci, I feel like I've done that already. Graph the asymptotes, check. Give the equation of the hyperbola in standard form, the eccentricity and the endpoints of the lattice rectum. So yeah, so the eccentricity is just C over A, so that's 2 root 10 over 6, so that's like root 10 over 3. Yeah. Sure? over 3 is the eccentricity. And then the endpoints of the latus rectum, well, if I draw in the latus rectum now, it's just like this very short segment here, and then there's another one over here. They go, again, through the foci, sort of perpendicular to the line through the foci. And basically, what we learned is that, like, you know, b squared over a will sort of do that for you. I guess these are your sort of two options for finishing off this problem, and then we'll stop. Is you could just do it by plugging in. So I don't know what that point is, so I call it x. But I do know that the y coordinate is 2 root 10. So one thing you could just be like is when y is 2 root 10 in general, x is what? That will give you basically that point that I want. And if that's the equation of the hyperbola, you could just do that, right? So when y is 2 root 10, you would get 40 over 36 minus x squared over 4 equals 1. And I guess I could just finish this off, right? So what is that, like 10 ninths? So 10 ninths minus x squared over 4 equals 1. And then that means that x squared over 4 is 1 ninth. And so x squared is 4 ninths and x equals 2/3. And since x equals 2/3, my alternative was to do it via formula. Via formula, it's b squared over a. And b squared over a in this case is 4 over a, so that's 2/3. But either way, knowing that that little thingy is 2/3, I can now say that the 4 points are like this point here is 2/3 comma 2 root 10. Writing in green is always pretty bad. This point is negative 2/3, 2 root 10, etc. And so the 4 points are plus or minus 2/3 comma plus or minus 2 root 10. Okay. And those are the 4 coordinates of the 4 points of the sides of the latus rectum. Okay, that should be good. You're going to finish the rest of the packet by yourself. Good luck. Goodbye.